More than 150 million tons of manure a year put German farms into the energy business, producing electricity, heat, and renewable gas on site. That scale also drives a dispute. Cow manure, organic waste, leftover food, and post-harvest residues are collected, crushed, mixed, and pumped into large digesters, then sealed inside airtight reactors. On many farms, the gas feeds combined heat and power units, or is upgraded to biomethane. The chain begins with more than 150 million tons of manure each year. That yearly manure flow points back to an older gas source. In oxygen-poor mud, dead plants rot and release flammable gas. The bubbles rise through dark water and the surface keeps breaking. Inside that sealed chemistry, microbial communities work without oxygen, splitting organic matter step by step. The first frame is swamp gas, not a farm reactor. The second is history. Alessandro Volta linked swamp gas to methane in 1776. By 1859, one of the first anaerobic digestion systems was built in Bombay, India. In 1895, gas recovered from a wastewater treatment plant in Exeter, England was lighting street lamps with yellow light. That is the shift from a natural seep to a controlled source of fuel. Today, biogas is gas from manure, food waste, crop residues, or sewage sludge decomposing in oxygen-free conditions. It is usually 50 to 75% methane with carbon dioxide, water vapor, and other impurities mixed in. Methane matters because it burns, generates electricity, produces heat, and can be upgraded into biomethane. After carbon dioxide, hydrogen sulfide, and moisture are removed, that biomethane can enter the gas grid. A mixture with that methane share can be cleaned, measured, and moved through existing pipelines. The IEA puts Germany's combined biogas and biomethane output at about 329 petajoules in 2024. That 329 petajoule result sits on a broader structure. Germany combines large-scale livestock farming, strong renewable energy policy, and a grid that needs flexible power during the energy transition. Many countries have manure and crop residues. Few turn them into a biogas sector. Since 2000, the Renewable Energy Sources Act, EEG, has offered feed-in support for biogas and other renewables. That gave farmers and businesses a reason to buy digesters, generators, pipelines, and gas cleaning systems. It also mattered operationally. Biogas plants can ramp output on schedule, unlike wind and solar. Germany is now the world's largest biogas and biomethane market, with more than 10,000 plants and about 87 terawatt-hours a year, far above many other European countries. That annual output needs fresh feedstock every day. In Germany, much of it starts in dairy barns. As of May 2025, the country had about 47,700 dairy farms and more than 10.3 million cattle. In 2024, dairy cows alone numbered about 3.6 to 3.7 million, close to Berlin's population of about 3.9 million. Most German dairy herds are Holsteins. Their day starts with a mixed ration of grass, corn silage, hay, grains, and supplements, and the silage smell stays in the feed lane. In the EU, average milk yield passed 8,100 kilograms per cow a year in 2024. That output demands water, space, airflow, clean walkways, resting areas, and hygienic milking zones. Fans drone overhead. Milking units pulse. Then comes the second stream. One mature cow produces about 25 to 50 kilograms of manure a day, depending on body weight, diet, and whether the count includes solids or liquid slurry. On a farm with several hundred cows, that becomes tens of tons every day. Liquid slurry matters because pumps can move it into farm digesters, and this flow arrives daily, not only at harvest. From the wet alleys, manure moves into collection and storage, then toward mixing and the anaerobic line. The next node sits under the barns. Channels, buried pipes, and pumps take slurry off the yard and into an equalizing tank. One intake line, several streams. That is the first filter on the whole chain. What makes manure fit for a reactor? Not removal alone, but collection, coarse cleaning, and a wetter, more uniform feed. The liquid fraction arrives first, with pump noise and a damp, sour farm smell hanging over the pit. Solid manure, leftover feed, bedding straw, and other farm byproducts come by a separate path. Then, operators pull out stones, plastic, and other large contaminants before they reach mixers or clogged pump inlets. That step matters early. Foreign material can damage impellers, and uneven solids can block steady feeding. Then, composition gets tuned. Slurry can be blended with silage, grass, and other organic waste because co-digestion helps balance carbon and nitrogen and improves flow. Some plants shred fibrous material, stir the mass, and check the feed ratio before loading. In the tank, the mix turns wetter, more even, and ready for the sealed reactor. The stabilized feed enters the sealed anaerobic digester, the next chamber after the mixing tank. Outside, it is just a round vessel with a tight lid. From the outside, the shell hides the chemistry. Inside, mixers and sensors keep the mass moving under control. No oxygen, no methane. The reactor is not storage. It is the first gas-making stage. Once the hatch closes, oxygen is stripped out, and methanogenic archaea can start working only in that oxygen-free space. They are a specialized group within the archaea domain, and they produce methane, not ordinary bacteria. Hydrolysis comes first, when enzymes split complex compounds into sugars, amino acids, and fatty acids. Then acetogenesis, acetogenesis, and methanogenesis follow in order. Temperature, pH, retention time, and mixing speed must stay within range, because even a small shift can cut gas output hard. One bad reading, 1 weak stir, and the yield drops. With gas now forming above the sealed reactor, the next risk sits in the line itself. Raw biogas may be only 50 to 70% methane, so why not send it straight to the engine? Because the stream also carries water vapor, carbon dioxide, and hydrogen sulfide, moisture and sulfur attack metal surfaces and contaminate lubricating oil first. Gas collects under the roof, then passes a hissing cooling and drying line where condensate drops out, filters catch impurities, and pressure is trimmed. Only then does the flow enter the CHP unit. Methane burns, the engine drives the generator, and power goes to the farm or into the grid. After power generation, warm digestate keeps moving through the plant. Where does the residue go? Operators separate solid and liquid fractions, and the plant still uses surplus heat. Digestate still holds nitrogen, phosphorus, and potassium, so storage and spreading must stay controlled. The solid part goes to organic fertilizer or bedding. The liquid part stays in storage for irrigation and field use. Once the residue streams are separated, attention moves upstream to the reactor inlet. In Germany, the dispute narrowed to corn silage because it gives biogas plants a predictable feed flow. Why so much argument? Corn delivers a high biomass yield, stores well as silage after harvest, ferments easily, and supports a fairly even gas output through the year. The sour smell of packed silage and the dense, even rows in neighboring cornfields point to that advantage. Then the contrast appears. When too many plots in one district shift into energy corn, neighboring fields start to look alike and field edges begin to shrink. Ecological value then depends on substrate origin, because those shrinking edges leave less shelter for insects, birds, and small organisms. In Germany, that land use argument reaches the plant gate too. Biogas collects in the plant's gas space and waits. When wind drops or solar fades, operators start the engine and feed power into the grid. That stored gas makes output more controllable than wind or solar. The sequence is simple. Gas rises under the cover and the generator starts. A low engine hum fills the hall. Heat from the engine and exhaust returns through hot pipes to the digesters, or moves on to barns, greenhouses, and nearby rural homes. One feedstock stream gives 3 outputs: electricity, heat, and captured methane. Waste handling matters just as much. Manure, liquid slurry, crop residues, and organic waste enter sealed digesters, not open pits. The sharp smell of exposed manure is largely gone, water pollution risk falls, and methane stays inside. Farmers sell electricity, heat, or biomethane, and local technicians, drivers, and service firms gain work. The cycle starts with one action. Manure and slurry pass through closed lines into the sealed digester. Once sealed digesters were already part of farm routine, the German debate shifted. Operators now ask a different question. Not how many new plants, but how to tune the ones already running for local demand. That means less dependence on maize grown for energy and more daily feedstocks from manure, crop residues, and organic waste. Older units can be retrofitted for biomethane, tighter heat use, and faster response beside wind and solar. After carbon dioxide and hydrogen sulfide are removed, that gas can meet grid quality or stay local for boilers. For the plant owner, heat is no longer a side stream. It goes first to the digester, then to barns or nearby buildings. A compact farm unit cuts methane from slurry and sends power and heat back on site. By evening, one shed still stays warm. That warm shed scales into a larger map. 7 countries first. Germany, Denmark, France, Italy, the Netherlands, the United Kingdom, and Sweden already run biogas plants on manure, food waste, crop residues, and wastewater, with Germany still the biggest hub. The International Energy Agency tracks biogas and biomethane separately. That split matters. Biogas stays concentrated in Germany, while biomethane, cleaned for gas grids or local gas use, grows in France, Italy, Denmark, and the Netherlands. Outside Europe, China and the United States use large plants on livestock farms, at wastewater treatment works, and on landfills. India, Brazil, Indonesia, and South Africa follow with strong potential from abundant organic waste. The feedstock changes, plant size changes, but the output stays practical: electricity, heat, and renewable gas. 7 countries, then 2, then 4. Beyond fuel output, the accounting turns harder. Each year, billions of tons of fertile soil leave the field, and carbon from crop residues returns to the air, 1/3 already degraded. The Food and Agriculture Organization puts roughly 1/3 of the world's soils in that category after millennia of intensive farming. First, a cultivated field still looks orderly from above. Then the surface shows a dry crust, dust lifts behind the machinery, and water runs across the top instead of sinking in. Across parts of Africa, South America, and Australia, repeated tillage and clearing have pushed once productive ground toward nutrient-poor, hardened surfaces. That upper layer forms slowly from roots, microbes, and decaying matter over hundreds of years, but intensive seasons can strip it away in only a few cycles. As erosion removes organic matter, the soil loses pore space, infiltration drops, and the field stores less water between rains. The carbon balance fails at the same time. When stalks, husks, and other residues decay or burn, the carbon plants captured returns to the atmosphere as carbon dioxide and methane. That sets the technical task for everything that follows: restore structure, recover water retention, and move waste carbon into a long-lived solid form. Biochar redirects that pathway through pyrolysis, a low-oxygen heating step that turns biomass into a stable, carbon-rich solid and lets soil hold that carbon for hundreds to thousands of years. That long-lived carbon has an older proof. Modern fixes, fertilizers, irrigation, carbon capture either cost too much, demand too much energy, or solve only one slice of the problem. So scientists turn toward the Amazon basin, which covers about 7 million square kilometers and spans 9 countries. Its tropical soils are naturally leached and nutrient poor because rainfall strips minerals from the upper horizon fast. On a map that large, the Terra Preta patches look local. They do not disappear. Terra Preta means black earth. The contrast is immediate: loose, dark soil beside red-yellow tropical ground. These patches hold fertility for hundreds, even thousands of years. Soil studies and archaeology link them to ancient indigenous communities that heated wood, leaves, and agricultural residues in low oxygen, then mixed the char into the earth. Not ash, stable carbon. Today, that ancient material is being revived for sustainable agriculture and a circular economy. That dark residue can follow 2 very different paths. Both biochar and charcoal are black, lightweight, and made by heating organic material. The resemblance stops there. Charcoal is tuned for burning, high heat output, and sustained combustion, while biochar is made to stay in soil for hundreds to thousands of years. Under a microscope, its carbon matrix opens into millions of tiny pores, left by plant cells and gases escaping during heating. Those pores hold water, retain nutrients, and give soil microbiota sheltered surfaces to colonize. Fuel charcoal releases most of that stored carbon during use. Purpose changes everything. Most of biochar's carbon stays in the ground instead of returning quickly to the atmosphere. So technicians judge it by stable carbon share, ash content, and acidity, because color alone cannot distinguish it from fuel charcoal. Then crews work the finished material into soil instead of burning it. Long before biochar is spread into soil, its composition is already taking shape in the feed yard. Wood chips, straw, nutshells, dry branches, and other agricultural residues do not enter the process as equivalent material. Crews collect them instead of burning them in open fields, transport them to the plant, and meter them onto conveyors. The trucks matter less than the input they deliver. Then high-capacity shredders cut wood and branches into a more uniform fraction for the next stage. Particle size affects later heating, and feedstock type affects the chemistry of the char itself. Biochar properties do not begin in the reactor. Hardwoods usually produce a biochar richer in stable carbon, while agricultural residues leave a product with a higher mineral share. Straw and rice husk often generate more ash than wood chips, so the final material can behave differently in soil. In several countries, this route has also reduced the open burning of rice straw on fields. By the loading hopper, the shredded biomass looks even and ready, but the differences set at the start have not disappeared. Even after size reduction, each chip, husk, and stalk still carries water inside its cell walls. That moisture is expensive. Evaporating 1 kilogram of water consumes about 2,260 kilojoules of heat. If wet biomass enters the reactor, a large share of input energy goes into steam, not into carbonization, so plants dry the feed first. Large rotary dryers keep the biomass moving through a drum while hot air passes across the bed, and a visible stream of vapor rises as moisture leaves the material. The feed becomes lighter, more uniform, and easier to heat in a predictable way at the reactor inlet. Many facilities cut moisture to 10 to 15%, and some send excess heat from pyrolysis back to the dryer to reduce outside energy demand. Before reactor feed, the target is 10 to 15% moisture. After drying, the feed no longer loses energy to water, and the next constraint is the reactor atmosphere itself. With oxygen reduced to almost zero, operators heat the biomass from 350 to above 700 degrees Celsius. No open flame. Inside the sealed vessel, only a dull mechanical hum remains while the dry mass darkens. This is the key contrast. In air, wood burns to ash, but here it decomposes under controlled heat. Hemicellulose starts breaking down before cellulose, while lignin decomposes across a broader temperature band, so the organic matrix does not collapse in one step. Cellulose, lignin, and other complex compounds split apart and leave a stable, solid carbon framework. Natural coal forms over millions of years. This conversion takes hours. As temperature rises, the char usually becomes more porous and more stable, but the share of solid residue falls while gas output increases. Modern units use temperature and pressure sensors for automatic control because small shifts change both yield and carbon durability. From this darkened carbon scaffold, volatile components keep leaving the reactor and move into the next loop. The char is only one output. The next stream carries heat. When biomass is heated, it releases methane, hydrogen, carbon monoxide, and volatile organic compounds. Those gases and vapors move through sealed piping and condensation units instead of escaping into the air. Carbon monoxide is toxic, so tight seals and leak checks are essential. After cooling, part of the vapor condenses into a liquid fraction, while the rest stays as non-condensable gas. No flare-up, just routing. One portion of the recovered gas is burned at once, sending heat back into the pyrolysis reactor and cutting outside fuel demand. That same flow, which leaves as a byproduct, becomes the reactor's own heat source in the next step. That is why many modern units run as near closed-loop plants. Some technologies also separate bio-oil, a liquid bio-based fuel used in industry. Experts therefore describe biochar as a dual-output process. Agricultural residues become energy and durable carbon storage. While part of the pyrolysis stream leaves the line as recoverable fuel, a solid residue remains in the reactor. In the field, that residue can slow water loss and keep dissolved minerals closer to the root zone, but that effect starts one step earlier. After many hours of heating, the remaining biochar is a light black material with very high carbon content. Cooling reveals the key detail, a rigid matrix cut through by millions of tiny pores. This pore network creates a large internal surface area, which helps the material retain moisture and mineral nutrients more effectively than many natural soils. Before application, producers often crush the char into smaller particles and charge it with compost, organic fertilizers, or beneficial microorganisms. Fresh biochar can temporarily bind available nitrogen, so preloading it with nutrients reduces that risk and lowers fertilizer demand. Cooled biochar waits before application. The next question is how long that carbon stays there. The next step is the soil itself, because solid carbon from pyrolysis matters only if field conditions keep it there. That is the real threshold. Matte black granules enter dry topsoil, and much of their carbon remains in a condensed solid form. Without that stability, ordinary organic matter decays and returns carbon dioxide or methane to the air. The material looks almost inert. Inside each particle, a pore network slows water loss near roots and holds dissolved nutrients longer. That cuts fertilizer loss and gives beneficial microbes protected internal surface surfaces to colonize. Amazonian terra preta still contains charred carbon centuries after deposition, showing how long the stable fraction can persist. This is why biochar appears both in arid parts of Africa and the Middle East, and on depleted fields in the United States and Australia, and why carbon credit schemes depend on measured soil stability and steady use in the field. Long soil storage starts earlier, inside the plant. Before a single batch reaches a field, the entry cost already climbs around the reactor, the gas recovery loop, and the temperature controls. That barrier hits small farms first. The costs start early. Then the material chain tightens. Wood chips, straw, and nutshells must be collected, sorted, and dried before feeding, and wet straw throws off heavy steam while the dryer spends heat removing water. If moisture stays high, efficiency drops fast. Heat is lost. Inside the reactor, the window stays narrow. Operators hold temperature and oxygen low for pyrolysis because extra oxygen or the wrong heat profile can turn biomass into loose gray ash instead of stable biochar, with hot metal at the outlet and dusty residue below. One error ruins it. Quality also shifts with feedstock. Straw char often carries more ash than woody char, and this batch spread helped create certification schemes such as the European Biochar Certificate and IBI standards. Weak roads and unstable biomass collection raise costs from preparation to delivery. Collect it, sort it, dry it, feed it into the reactor. Once operators install the reactor line, location decides viability. If straw and prunings travel too far, handling costs rise fast. The best projects sit beside a steady source of residues. There, reactor heat can dry the next batch, and nearby fields take the product back. That is the contrast. One stream is waste, the other is soil input. Biochar links soil degradation, climate pressure, and rising organic waste in one material flow. It turns dry branches, straw, and agricultural leftovers into a porous amendment. It holds water, supports fertility, and stores carbon underground. Amazonian terra preta is the historical reference, but cost, equipment, and standards still limit scale. Those same residues can keep carbon in soil for hundreds to thousands of years.